due to the large volume, uh, volume in the extra dimension. So the R weak in terms of the length scale is around 10 power minus 17 meters, whereas R extra dimension is around the gravity scale would be current around 1 mm. So which is around 10 power minus 3 meters. So again we are reintroducing the hierarchy, but in terms of length scales instead of energy scales essentially. So we are not solving really the hierarchy problem. It's like a reformulation of hierarchy problem. Now, of course, there are great people who don't agree completely with it. They don't like this idea and everything, but for a contrarian viewpoint, famous guy called Mikhail Shipman. So I advise you to listen to his videos, seminars on ADD models. Okay, on Schiffman and Dwally have some papers also. So okay, so look at Schiffman. I think some of them may be available on YouTube. Okay? As seminars. Okay, Mikhail Shipman. Okay, so now today we come to another model, extra dimensional model, which currently we think is the right model to look at. It's the correct extra dimensional model. Many of us believe to actually look at. This is proposed by two people, Lisa Randall and Raman Sundar. Called Randall Sundaram models, or also in short called RS. So what does RS model geometry construct? Geometry of extra dimension to solve the hierarchy. Now this is extremely very interesting scenario actually. So what does it contain? So what does it contain? So what it contains, uh, they use technology from string theory, some part of the technology from string theory. They also use some technology coming from some inspired by string theory, but just ordinary gravity, cosmology essentially, just from cosmology, ordinary gravity. So it's a combination of two things. The things they use from string theory are essentially like brains. Okay, they use the technology of brains essentially. So to start with an extra dimension, compactified. Start with an extra dimension, compactified, single extra dimension. You don't need to have more than two or more than one or something. So it's just a single extra dimension. Compactified on a circle. And then you mod it, because as I said, if you want to put fermions, you need to mod it essentially. So you need to put Z2 symmetry essentially. So the extra dimension which is a circle is now becomes a line. Okay, it's a line because you identify each point with the other side. Okay, and then y goes to minus y. Okay. So this becomes this, so this just becomes, you can write it on the line. Y goes to minus y. So you have an extra dimension which is nothing but a single line with two singular points at y is equal to 0, y is equal to 1. So this is a singular point or orbifold fixed points. All this we have seen last time actually. So these are singular points because and if you put any point here, because there's a delta function sitting here, there's a delta function sitting, okay. These are singular because at this point y goes to minus y has several solutions. Y is equal to 0 is not real. 0 is equal to minus 0. Same thing as y is equal to pi r is equal to pi r is equal to minus pi r. So that's the reason why they are called singular points. So they don't have any meaning in the real sense. So 0 is equal to minus 0 doesn't have meaning. So it's singular essentially. So at these two singular points, you have extended spacetimes. Okay, extended spacetime. So these extended spacetimes, which are both four-dimensional. So it's explicit from here. And these extended spaces are called branes. These are called specifically D3 branes. D3 branes are string constructions because string theory lives on. It's not a field theory. Okay, so it's an extended object. It's not a point object like ours. Okay, so these are extended objects. They are solitonic. So in field theory, these you can think them as some extended solitonic objects essentially. Okay, consider them to be some solitons. I refer to you. I'll put it up in the Teams page. There is Shaki brain sync field theory. Okay, there's a within lecture notes by Shaki brain sync field theory. Okay, I'll put it up in this what do you call it? Our Teams files thing. But if somebody, if he wants my full repository, just write to me an email and with their Dropbox email ID. Okay, I'll just share the Dropbox because I have in next sections all the references and from which all I took market right essentially. So branes, so these are extended objects. So in field theory, they are essentially like solitons. What are solitons? Solitons are classical objects of solutions of nonlinear differential equations. So if you have nonlinear differential field equations which are nonlinear, solitons are localized in space. Okay, these are localized in space. So meaning if you choose a space-time point, okay, they are localized in space. If you similarly you have localized in time, they are called instant time, instant also. Okay, they are localized in space. Wave solutions. So wave equations, you take your field equations, okay, solve them, and these are essentially classical objects. So they are quote unquote classical objects. And around these classical objects, you can have some fluctuations. That's a different thing. It's like wave or something. No, you can have these solitons, and then you can have small sub fluctuations around them. Essentially, so those are called brane fluctuations and so on. But that's a different thing. So these are take these wave equations, solve them classically, and you find localized solutions in space. These are localized solutions in space. Okay, this happens in your ordinary uh, uh, wave equations also, hydrodynamics or anything essentially. So solitons were discovered that way. You see a wave which is traveling, which it doesn't change its shape, and it's moving in time. Okay, that's how they have been discovered actually. Okay, so the important features of solitons are essentially they are localized and quote unquote their quantum solution. You can build states also, soliton states and everything. But for the present, let's just take them to be as a classical solutions. Okay, in principle. And now you have this huge solitons. These are they are not compact. These are non-compact. Okay. So imagine that this space-time is living on a solitonic thing. On this at y is equal to 0, it's localized. Okay, our space-time is some sort of like a soliton-like object on a it's a brain. It's living at y is equal to 0, and there is one more thing living at y is equal to pi r. Living at y is equal to pi r, and between these two space-times, there is a bulk with only gravity in it. Between these two space-times, there is bulk with only gravity. I don't know. Did you get the picture? Essentially, that you have your space-time here. Okay, you have your space-time which is living on. There are two space-times. This is a x mu which is living here, which we call it as the hidden brain. And this is something called the visible brain. Visible brain is a brain in which we all live. All the standard model particles live essentially. So this is also x mu. This is also x mu. Two x mu's are living on two solitonic-like brains essentially. Okay. So this is your visible space-time. This is your hidden space-time. So there is another space-time, okay, which is living on another brain. This is our brain essentially. In between these two brains, there is something called a cosmological constant, which is with a negative sign. We'll come to it in the second picture. The cosmological constant. There is only gravity. We'll come through all these features one by one.
So if we are moving from one brain to another, only time coordinate is changing.
Y is changing. Time coordinate is everywhere. It's here, it's here. X mu is here, X mu.
They are two different.
Y is changing.
But there are two different coordinate systems, right? Because x mu remains constant in both.
This is the same X mu. This is also the same X mu. But one X mu is localized at y is equal to 0, one X mu is localized at y is equal to pi r.
So y is a coordinate system which is separating brains.
Y is the coordinate, only y is separating these two brains. Only the extra dimension is the separating these two brains.
Yeah,
Fine?
because So why is the extra dimension x
Yeah. So here there is only gravity, and all the standard model fields live here. So standard model fields live here. So we are only sensitive to this one. Now the geometric picture is quite confusing. Okay, it's very complicated and looks simple. Doesn't look simple. Let's just write down the metric. Then you feel comfortable. Okay, the metric is not so complicated. Okay, I'll come back to the geometric picture in a second. So let's just look at the metric for ADD models. So how did we write the metric? So ds square is equal to dx mean minus r square dy. Okay, something. If so, this is dt square, c square is for 1, dt square, dx bar square. So r square d. Sorry, it should not. If I put in r square, then it should be dy square. So this is called flat extra dimensions. Or if you want, we will write it as r square d phi square. Okay, r square d phi square. These are called something called flat extra dimensions. Flat. That means the y coordinate behaves exactly like rest of the space-time coordinates, except that it would be compact or something. If it is compact, we will put a radius and an angle corresponding. Okay, but it's exactly like this: dx square, dy square, dz square, dy square. Okay, dx1, dx2, dx3, dy. It has the same metric. It exactly behaves like a space-time coordinate, ordinary space part of the ordinary metrics. But let me consider a metric which is a bit more complicated, which distinguishes our space-time with the extra part. Our space-time should be different with the extra part. Okay? So that kind of metric now what is the difference? What is the difference? Up to this point it's the same. It looks like the flat extra dimension. But our part of the g mu, or eta mu, is multiplied by an exponential factor. And this exponential factor depends on the extra dimension. Okay? So you cannot, so this factor, this is factorizable. That means we could write functions as products of, okay, phi of x, phi of y. Okay? Now here you see, this one is a complicated function. The function exponential sits in front of the dx mu. So our metric itself, our part of the metric, is multiplied by the extra dimension part. Okay, there is an exponential factor sitting. It's very similar to conformal. I don't know if you have looked at conformal metrics. I think you may have looked at it. Yeah, exactly. This is conformal. Conformal doesn't distinguish between extra dimension and this one. Everything is multiplied by the same factor. Okay, but here you are saying there is a conformal factor only for the dx mu. These metrics are called non-factorizable because you cannot factorize x and y. So this one has a metric G mu visible. Here G mu visible is equal. Okay, let's write. So this is ds square is some capital GML, capital GML. So capital is 5-dimensional metric. Okay, 5-dimensional. So visible would be what? Visible would be x mu, normal x mu, but the y coordinate is called pi r. And G mu hidden, this brane G mu hidden would be x mu, y coordinate is called 0. So there is an x mu here, but y is equal to 0. There is an x mu here, y is equal to pi. Only one extra dimension. You don't have multiple extra dimensions or something. Huh?
Sigma.
Sigma is just some function of y. Sigma is just some function of y. We'll determine what it is. Sigma is some function of y. We want to be, yeah, more accurate. It's some real function of y essentially. Okay, but we can determine.
Can a visible brane live at y equal to 0?
You can, but the geometry would change. As you will see, the reason is because you can in principle change it, but the geometry should change because you want something called the warp. This sigma is called something called the warp factor. And that's the reason why these are called warped extra dimensions. Now, the sign of the warping is important. So the sign of the warping is, as we will see. So what happens is the warping should be such that it is gravity is very weak in our brain. Okay, the sign of the warping is very important. So if you modify the visible, okay, so the hidden sector brain gravity is very strong. So but it moves to the visible sector brain, it becomes extremely weak. Okay, so if you want a shape like this, it's fine. But if you want a Z2 version of it, you need to modify the geometry such that it. So that's the reason why I'm emphasizing y is equal to 0 is important, y is equal to pi. They are not symmetric. They are not symmetric. I'll tell you when you cannot make them symmetric, there is a signs difference. Okay. So let's write down the action. Action is equal to S gravity, which is essentially the bulk action, and the brain actions essentially. So S visible plus S hidden. Now the claim is that this metric is a solution of this equations of motion, this action. Okay, from this action you get Einstein's equations, and from those Einstein equations you should get this metric. But normally what we do is you do the reverse. You take this metric, compute all the connections and everything, and just show that it satisfies the Einstein's equations. Okay, so the geometry one constructs is essentially S gravity is equal to integral d power 4x d phi 5-dimensional metric root g 2m cube r plus lambda is some constant which is nothing, also called as the cosmological constant. So the 5-dimensional metric has a cosmological constant. Okay, it has a cosmological constant. Now it should be m square r, but there is an m because I wrote it as d phi. As visible will determine what these are essentially. D power 4x minus g. We have written already, this means g visible times some energy or some potential which is called d visible. It's on the brain. And S hidden is equal to integral d power 4x minus g minus hidden. Same thing, minus v hidden. This is some potential. Why we wrote potential? Because it should be some 4-dimensional scale of energy. Okay. Some mass scale essentially. Some. In a brain technology, in brain nomenclature, this potential turns out to be something called the tension of the brain. The tension of the brain is essentially the energy density of this space-time. The total energy is sitting on this of the space-time. Per unit volume, per unit whatever it is, essentially it doesn't make sense. Okay. So when you put it back into the Einstein's equations, you get one can do it, okay. But nowadays I think take that metric. You have this mathematical codes which turn all the Ricky scalars, all the Riemann scalars, everything they can give you actually. What are the codes called? I don't know. Riemann. Einstein tensor, and there is also Riemann convention and everything. No, these codes are called some Riemann.m or something is there. Some code is there.
Python file as well as mathematical.
Oh, Python is there. Hartle has a notebook. I use one by this person.
You have to just keep the metrics and it will give you all the Riemann tensor, Einstein tensor, energy moment.
Everything. Oh wow. Okay. Excellent. Okay. Anyway, one can use those, or it can actually calculate by hand. Okay. This is the solution. So first derivative of sigma should be equal to lambda by 2 power n cube. The second derivative is equal to v hidden r delta phi 12 q phi V visible are delta of phi minus phi by 12. So if you solve this, you get sigma. No, this is r square, isn't it? R mod phi root of minus lambda by 24. So this normally one writes sigma is equal to kr. Sigma is equal to kr. Okay. This is the k. K is this value. This is the plant mass lambda. Okay. This gives you the R factor. This derivative with respect to phi, by the way. This is the derivative with respect to phi. With respect to y. Okay. Y or phi. So this has only solutions because this has only solutions which should be real when lambda is negative. So that means the cosmological constant should be negative. So spaces or universes with negative cosmological constants are called anti-de Sitter spaces. Now we can introduce the notation k is equal to root of minus lambda by 24 m cube. K is some constant which appears in the Borg factor. So sigma is equal to 2k phi. So that instead of writing this thing, we can write it.
So the information regarding y is contained in R and phi in sigma, right?
Instead of information about y,
Explanation.
y is equal to r phi. Y is equal to r. Y is equal to 0 means phi is equal to 0. Y is equal to pi. Pi r means phi is equal to pi. Instead of just writing in terms of dimensionless angle variable. That's it. So the space between the two brains is an anti-de Sitter space. These two.
Yeah.
These two we wrote it from the metric. Oh, sorry. Here there is sigma is equal to this. Sorry, this 2 is not there. In the metric there is a 2. Sorry, sorry. This 2 is not there. In the metric there is a 2 actually. Yeah. It is 2 sigma of y, no? The metric contains 2 sigma of y. Okay? Yeah, so this is that. Now that we have a form for sigma, I can differentiate it twice, and so that I can determine what is V hidden, what is V visible. So this factor we call it as k. You can write it as k. So now this is implies. So let's equate the delta parts. So if I equate these two equations, and match the delta parts, so V visible and V visible. Is it right?
This derivative is with respect to phi, right?
Derivative with respect to phi.
In double derivative, it wouldn't be there, right? It would be at least then phi square should be there.
No, there is a phi here. But the delta will not go away, no? But with boundary conditions, it's a modulus of psi.
So this sigma is basically
It's not on all over space, no? Essentially, it's with
looking at phi.
at pi is equal to 0 and pi is equal to pi r. Okay? Is that fine?
Derivative of delta function.
Derivative of delta. No, the derivative is equal to the delta function.
In the second derivative,
It's a derivative of the modulus, right? Essentially. Derivative of the modulus.
then again you have to take one more derivative. Then derivative of delta function should come.
Derivative of the delta function. Yes. No, this is just delta at phi and delta is equal at phi minus. It is just the endpoints essentially at the singular points.
Okay.
Okay. So these, I think, you were asking, right? Essentially, why it should not be symmetric. The energy density on both the branes is opposite to each other. Okay, there is some negative sign essentially. If it is the same, then it's symmetric, but there is a negative sign. The energy density should be opposite to each other in sign. That's the reason why the brane tensions are opposite tension branes. So what you have, finally you can derive m Planck square, 5 dimensions. Okay, 5 dimensional m Planck square is equal to, or this is your 4 dimensional m Planck square is equal to k 1 minus e power d k r. This is your work factor. So the extra dimension is not large. The extra dimension is very, very small. The dimension of the extra dimension is very small, and m Planck, and this is also very close to m Planck. K is also very close to m Planck. So essentially, m is very, very close to m Planck. So 5-dimensional Planck scale and the 4-dimensional Planck scale are very, very close to each other. So there is no separation of the scales. Okay, you are not bringing down the Planck scale very long. Okay, this is a very small factor. Suppose if k is positive. Okay, kr is around 11 or 10 or something. So this is a factor 30 sitting in exponential. So this gives me, this is a very, you can throw this number. K is already of the same order as M blank essentially. Okay, if K is of the same order of M blank, you can throw away. Kr is order 10 essentially. Kr is order 10, say for example, order 1, we call it as order 10. So Kr is order 1, so R is order 1 by 10 essentially. So the difference between the M blank and K would be of the M blank and K would be roughly the same order. Okay, maximum up to order 10 or something. So the scale, change in the 5-dimensional scale and the 4-dimensional Planck scale is very minimal, purely because of the exponential factors. The suppression in the scales is coming because of the exponential factors. The suppression in the scales is coming because of the exponential.
We take flat metric.
This is not a flat metric. 5-dimensional metric is not flat. 4-dimensional metric is flat.
You said, so this is non-factorial. Starting you took the two kinds. One was flat and one was non-factorial. So if I take flat one.
If you take a flat one, this
Yeah, that
function
will
won't
not be there.
This will not be there. There will be a large volume factor. There won't be an exponential factor. You directly get a r cube or something like that. R1 2n or something. 2n plus 1. So that's the reason you need a very large volume to suppress the Planck scale to the weak scale. Now, 4-dimensional Planck scale and Mach scale are same, but if you want a TV scale, now you see this can be a Planck, but if you want to get a TV scale out of this, it's always multiplied by this factor. If you can somehow make this factor work, then you are in business. That's the basic idea. If you can make this factor work, then you are in business. Now, now the resolution to the hierarchy problem is actually nice, but it is not easy. Okay, I mean in the sense I had to. I'll just show it to you how it's done. So this is okay. Let me just finish the setup. The setup is you have two negative tension branes. So this has a tension T, which is positive. This has a negative minus T. There is a warp factor. It is an ADS space, so negative cosmological constant. And this we call it as the hidden sector brane, and this we call it as the visible sector brane. And that is pretty much it. And this gives you a 5-dimensional metric. Gmn is equal to e power minus 2 minus 2 r hit minus 2 r phi k eta mu minus d phi square. This gives you metric. Now, in this metric, I am going to put here all my standard model fields. All my standard model fields are going to sit here. So that means I have to write, if I have to write all the standard model fields, if I write them as 5-dimensional fields, they have to be multiplied. The metric is this metric times this metric. So this part. Ah. Or let me put it as GB. Okay, so let's try to write down the metric. Okay. So let me just put the Higgs field, integral dx per 4, and on the visible field sector. I just write down the T mu of the Higgs field, which is nothing but all the Lagrangian essentially. Now G visible minus is equal to Gmn x mu y is equal to 0. I put that 5-dimensional metric. Okay, and take the det. Okay, det minus sign square root. So that is equal to e power minus 4 k r phi. Now G mu visible is equal to e power k r phi 2 k r phi eta mu. We wrote down, we just wrote down this. Okay. So the product of these two sitting here gives you minus 2 k r phi. Minus 2 k r phi. So what it does, it multiplies the kinetic term with minus 2 k r phi. Minus 2 k r phi is multiplication to the kinetic term. Because I had to put it here and then k r phi. So I had to do canonical renormalization. So canonical normalization, I have to move to the fields to the canonical basis. That means the kinetic terms are canonical. That means they don't have any factors in front, they are 1. If I do that, if I define h goes to e power k r phi h S is equal to integral d power 4 eta mu visible del mu h whole divided del mu h minus e power k r phi m whole square h dash h plus lambda h dash h. So what is happening when you do this thing? Whenever there is a h dagger h, it cancels everything. Okay, h dagger h, you can always rotate everything. If you have its unity, right? Essentially contribute. But if there is a constant term, if there is a constant term sitting in front of you, that still stays essentially. Okay, because so whatever you do, all the rotations will be there, but the canonical quanta, if you move it into the canonical basis, that cannot escape this kr by definitions, minus kr. The moment you change this one, this will pick up a minus kr by whole square, multiplying the m times this. So what does it mean? That your effective m square is actually e power k r phi. Suppose this k r into factor is not there. Your m would naturally would be what? M Planck square, because we argued it is not protected by any symmetries. It's a bare mass term in your Lagrangian. So any bare mass term will sit at the M Planck scale essentially. Okay, it should be sitting at the M Planck square. Now it sits at M Planck square. Your small m is nothing but your M Planck. But this M Planck is multiplied by an exponential factor because of the Mach factor. Your M Planck is multiplied with exponential factor, which is the Mach factor. So what you see effectively on a visible brain is e power k r by times m square on the visible brain. So that means if this is M Planck square, the bare mass term is M Planck square, the effective thing would be if you multiply the M Planck with order 10 entry, order 10, it will become 1 TeV or less than a TeV essentially. Whatever mass you want. Okay, because of the extra dimension, so it is not as easy. You are not bringing down the Planck scale. You are having a very small extra dimension, very close to the Planck scale, order 1 by 10 or something. Okay, 1 by 10 is a, so it's not even 1 ml. It is Planck scale extra dimension. Okay, within order 10, order 1. Okay, you have a very small extra dimension. But because of the exponential warp factor, in this extra dimension, in this small extra dimension, you have huge energy density such that there is an warping of the gravity. Because of the warping of the gravity, the Planck scale in the effective brain appears as suppressed by the warp. So it comes out to be around 1 TeV. If I take R, Kr is around 11 or 12, I think if you take it around 12 or something, you get it essentially. So the metric is only multiplying the derivative terms, remember that. Okay? So this is the other one which is Other things, whatever it is, constants and everything, it can be absorbed. You can remodify them essentially. But what you cannot escape is redefinition of these fields. The moment you change your H, canonically normalized, and put it in terms of visible sector, this is what we see essentially. In terms of the term what we see is what we see finally essentially. Otherwise, these parameters can be always be redefined essentially, lambda or whatever. Okay. So that's how you solve the hierarchy problem. Are you convinced? Is it a solution to the hierarchy problem? So you start again with the bare Lagrangian. Okay, you start with the bare Lagrangian, and the bare Lagrangian is suppressed by an exponential one. You are convinced?
Yeah, mass scale is pushed.
Mass scale is pushed.
It's kind of artificial.
Huh?
Artificial, like putting something
By hand. But okay, so the big thing is that you are not reintroducing any hierarchy. All the entries are order 1. Okay, you are not reintroducing any hierarchy. Okay, so why do you call this as ADS? Because you have a negative curvature. If you have positive curvature, you call DS essentially. So this is interesting because we call this what thing. So people think that it has a connection with. This is a 5-dimensional analog of a strongly coupled theory like ADS, which we will do in the next class or something. Now, what are the problems? This is too good to be true. Okay. This is too good to be true. The main thing is that one of the main problems. I'll list out the problems and then we'll discuss the solutions.
So how is geometry will locate de Sitter space?
De Sitter space in the sense that you want it will be opposite curvature.
So from visible to.
If you have a de Sitter space, it will be what do you call hyperboloid sort of. It's unstable essentially. Okay. De Sitter space will be positive curvature. This is negative curvature. So it will be open sort of thing essentially. You cannot localize. Yeah. You cannot have an ending to something essentially. It will be like changing teeth. Like you said, the first one, changing the brains. If you put the visible brain on the hidden sector brain and interchange, visible brain will be like in de Sitter space essentially because it has a positive curvature. Some problems. What does it mean? Gravity is always an attractive force. Gravity is not always an attractive force. Now, you have two brains located, one with positive tension, another with negative tension. Okay, T1 and T2. and they are fixed at certain points. It's very important that the entire space-time is fixed at x is equal to 0, y is equal to 0, and y is equal to pi r. They have to be stable there. These space-times have to be stable there, essentially. They have to be. So are these things stable under simple gravitational fluctuations? They should in principle, because negative tension brane is like an anti-brane essentially. Okay, so brane anti-brane also will attract, gravity is also will attract. They will come and should collapse with each other, and then fall off essentially. So this geometry, imagine that it's like again a fine tuning. Okay, it's again like a fine tuning. Instead of saying that, okay, typically fine tuning arguments, what do they say? It's like having, you take a needle, okay, you take a needle and trying to balance it on a table. That's a typical example we give you, right? You cannot balance a needle on a table because that's how it's not stable, because under small quantum fluctuations the needle will fall off. Now, but you're having a huge geometry and in gravity, it's not living anywhere. Essentially, it's in gravity, it's not in vacuum or something. There is always gravity. You cannot think of something which doesn't have gravity. In gravity, is this configuration stable? Okay, the answer is no, it's not stable. So for that, you have to actually calculate what are the back reaction in gravity. Okay, calculate the back reaction, and whether this radius over time will just shrink, and just fall. These two become one point. Okay, so is there a way of stabilizing this one? How do you stabilize this one? So there is a mechanism of stabilizing this one. By Goldberger and Weiss, which we will look into it in the next class.
On a given time scale, they can be stable, right?
But we have to live all over the universe, right? We are not stable anymore. And the universe should lie on this brain, essentially. Okay? If you are satisfied for an instant or something, then it's fine, essentially. But it should be stable at lifetime. So we have not covered this thing earlier, but I'll cover it right now. One of the strongest constraints on any physics beyond standard model comes from electroweak precision test. Now, what are these electroweak precision tests essentially? Electroweak precision tests are these measurements of mostly done at lab. I think we talked about it a little bit. These are this self-energy of ZZ, Z gamma, essentially W. So what they did was measure the decay widths and the masses of W and Z at very high precision. Okay, and then they have a bunch of observables essentially, like R, B, or C. So various observables essentially at the Z pole. Now, if there are some new particles, say for example, there are now some new particles. So that's all fine for the standard model. If there are some new particles, they will modify these loops because they will also go into the loops. They will also go into the loops. Now there is one parameters by Priskin and Takeuchi they introduced three parameters for electronic precision test. So these are called STU. So these STU parameters, I'll give you the definition in the coming classes. So these are linear combinations of these operators, essentially. Linear combinations. These are pies, right? These are the pies. The self-energies are called pies. So what happens is this, why I'm coming to the question essentially that why now this S parameter played a big role, okay? S parameter played a big role in ruling out technical. Okay, we didn't talk about strongly coupled theories. So the paper of Paskin and Takeuchi actually shows that electroweak precision test rule out any strongly coupled theories at the electroweak scale essentially. Okay, it's an actually nice paper but written very horribly. Okay, it is very fat and everything. Okay, but I don't know. Peskin has this. His textbook also is like that. Sometimes he overcomplicates things rather than simplifies things essentially. Okay, so he overcomplicates things, but there are other lectures towards STU. Okay, um, read those things essentially, where you can actually show why the S parameter rules out the technical. I'll cover it maybe in the next class. I'll try to cover it essentially. Now, why this is applicable to Randall-Sundram? Why this is a worry for Randall-Sundram? Like I said, Randall Sundram has a conformal factor. This factor is a conformal factor, and this conformal factor multiplies the weak sector or the visible sector essentially. So this conformal factor is multiplying the visible sector. So there is an e power 2 ky sitting in front of your visible sector. This thing essentially. So if you have such a thing, so whether you can apply, you would expect that ADS-CFT will come into play essentially. ADS-CFT tells you what? That if you have gravity, weakly coupled gravity in 5 dimensions or 4 plus 1 dimensions here essentially. This is a 5-dimensional law. Actually in ADS-CFT it is m times 6 dimensional essentially. Compact space, weakly coupled gravity. It is dual to a conformal field theory resting in n minus 1 dimensions essentially. Okay, lower dimension field essentially. So this should be conformal field theory which is strongly coupled essentially. So that means if you take a 4-dimensional picture, so this 5-dimensional picture, so this here this theory 4D theory which is standard model would be a strongly coupled theory. So all the resonances, all the KK resonances and okay, of the visible sector would be strongly coupling at the IR brane essentially. At the IR brane will be strongly coupled. So will it be a repetition of the Technicolor like scenario essentially? And it turns out to be true actually. Okay, as we'll see, once we do the KK reduction, I'll do the KK reduction in the next class essentially. turns out to be true that this is indeed a strongly coupled theory, and the constraints coming from electroweak precision tests are extremely strong. By far, you can escape this one. To escape this is very hard even now. There are several models. Okay, by far this is one of the strongest constraints on runners because it's purely a strongly coupled theory. Okay, and the third one is essentially flavor physics and everything. Okay, I'll come to it later on. So let me focus on these two, and in the next class lecture, I'll focus on stability, and if time permits, I'll also talk about electroemission test. And in the following lecture, I'll try to do localization of flavor physics. Okay. I hope I'll do that. And the last two lectures I'll see. I wanted to talk about axions or relaxia. I don't know what I'll do actually. Okay, let's do this. Okay, I'll stop here because it will take some time talking about the configuration. Okay, these two I'll stop.